All right, so first today we will talk about centripetal acceleration. And I actually have a demo I did myself to show you. So, what this is here is I took basically like a pie plate and I cut out the corner of it. So, I cut out one quarter of it. And what I'm going to do is, well, I can show you the start of it. So, I'm going to grab this ball and I'm going to roll it along the outside of it. Right, see how the ball's going to roll all on its own. And then when it gets here, what's going to happen? Is it going to follow path one and keep curving? Is it going to follow path two and go straight? Or is it going to follow path three and go outward? All right, so yeah, there's different thoughts. I could see one because it could continue to curve. Two, it's if you looked at its velocity right now or whatever, you could say it's going straight. And three, you can look at well, it's been pushing against the outside of the pie plate the whole time, so it's sort of pushing back on it or something. All right, well let's see this thing. I will play it. Absolutely, yeah. I went in number two. One more time. And the reason for that is, well, I mean, Newton's second law, if you will. Perhaps first, there's kind of inertia. So if you look at an object that's going around in a circular path, right, you could say at any one point, let's suppose it's right here, its velocity at this moment would be exactly in that direction, right? That's if you were to draw a tangent line here on this circle, you would say that's where its velocity is right now, right? And so as soon as the pie plate's gone, right, it continues with a constant velocity. As it's going around in a circle this way, the pie plate is constantly applying a force, right, pushing it toward the center of the circle. And so that keeps changing its velocity, right? It's got the force it needs to keep changing its velocity, whereas all of a sudden here it didn't have that force anymore, so it continues on a straight line, right? It could also ask a question like, what would happen to the Earth if the sun instantly disappeared or something like that, right? Well, it would go in a straight line. Right? Not that I think that will happen. The sun is a lot of mass. So anyway, if you wanted to look right now, though, right at the acceleration, right, as it's continuing to go in a circular path, that is the direction of the acceleration, right, toward the center. So at this point, there's v. And as it continues to go around at some later time, velocity would always be, like I said, perpendicular to the radius of this thing, or right, if you're drawing a tangent line, and the acceleration would always be right toward the center. And that's always the case as it goes around and around in a circle. So yeah, up here I kind of left it hanging, didn't I? For an object moving in a circular path, the acceleration is always toward the center. There you go. Ari, nice Canadian spelling there. Down here below, I didn't really like the one in the textbook. It seemed a little too much to it. So this is the simplest version I can find of it, just to show you how we get, because we need an equation if we're going to use this, right? So consider an object moving in uniform circular motion from point P1 to point 2. So these 2 points right here, you can see it's circular motion. We've got the same radius here at both points. And this is in some time interval delta t. So we can say that the object moves a distance delta s. That's what's indicated right here. So the angle, we'll call it phi. I never know if it's phi or phi, but I guess people say it different ways. They'll say phi. So that's the angle here that it actually travels in going from P1 to point 2. And this should be the same angle if we do a diagram right here, right? That's this one down below. So we can say we know V1 plus delta V has to equal V2, right? Another way to think of that is V2 minus V1 is delta V, but probably easier to just, because we're used to vector addition. So we're used to just saying if you have V1 and then you add some delta V, that should get you to V2. Now the claim is that this angle here is also phi. And the way that we know that is if you go from point O to P1, right? And then from O to P2, you've gone this distance here, this angle here, phi. But if you look at OP1 and V1, you'll know that V1 is perpendicular, right? Because the velocity is always perpendicular to um, the radius. And the same thing is true if we go from the point O to P2, well, V2 is perpendicular to that, right? So you can almost think of it like if you've just got um, the one that I've left here, OP1 and V1, and that's perpendicular, and you rotate that forward, right? Well, if V1 was perpendicular to OP1 and V2 is perpendicular to OP2, well, then it must be the same angle, right? The same angle between V1 and V2 it's gonna be the same angle. And knowing that, that means that this triangle here and this triangle down here are similar triangles, right? Because it's the same angle. And we know that the radius is constant. We also know that the magnitudes of the velocities, right, V1 and V2, are the same. So these are similar triangles. That means we can say the far side or the small side over one of the larger sides, right? Those two ratios have to be equal. So looking at this one here, delta V over V1 is the same as delta S over R. And that's what's indicated right here, right? You can rearrange that for delta V, and that's all that happens here, right? So that's V1 over R times delta S. So that means to find the acceleration, the acceleration is delta V over delta T. We can take that delta V equation and substitute it in there. And that leaves us with delta S over T, which is just V. And since V is constant the whole time, V1, or whether we write it as V1, V2, or just V, it doesn't really matter. And that gets us to this very important equation here, which is that the centripetal acceleration is just V squared over R. The other thing we might want to know is the period or frequency of something like this. So again, we're mainly dealing with objects that are in uniform circular motion, right? So they're going around at a constant velocity. The radius is the same. It's going in a circle. So we define the period as the time it takes for one cycle or revolution, if you will, if it's going around in a circle. The inverse of that, right, is the frequency, which is the number of times it goes around per unit time, right? The number of cycles. So often frequency is like cycles per second, and period is the opposite of that, right? It's how many seconds per cycle or revolution, whatever. Okay. So if we want to figure out the period and we're looking at something like here going around and around in circular motion, the distance that it goes when it makes one revolution, right? The distance is 2 pi r. That's just the circumference of the circle. The time it takes is what we've defined to be the period, which is just this capital T we're using. And now we have our equation we just got on the last page that says the acceleration, or I'm using a subscript here, C, for centripetal acceleration, is V squared over R. And V is just D over T. So there's the distance, we just said 2 pi r, and the time is capital T, or the period. We can rearrange that to get this over here. If you're given the frequency, right, since like I said, these are sort of reciprocal relationships here, F equals 1 over T or T equals 1 over F, whichever you prefer, then you can use that and you can rearrange this same equation for F. But, or you can just replace this T squared with 1 over F squared, which puts the F up on the top. So anyway, if you're trying to put together like a formula sheet or formulas you need, these two right here, I think would be the two biggest ones you would need. The centripetal acceleration itself, v squared over r, and this one here for centripetal acceleration. Just understand what it is for something to go around in like circular motion. Then you can use this here. So I'll look at a very quick example. It's actually quick because it's what's happening is pretty quick. You've got a carnival employee who likes to give people an adrenaline rush. So he runs the merry-go-round such that a child 3 meters from the center of the apparatus zooms by him trying to hold on with a velocity of 72 kilometers an hour. Calculate the centripetal acceleration of the child and the time it takes the child to complete one revolution. So the first thing, because we're kind of got mixed units here, the first thing I would figure out is just V. Because I'm given that in kilometers an hour, remember you just divide by 3.6, which means you're dealing with 20 meters per second. That's the speed that this is going around. We know that the radius of this thing is 3 meters, and that's all we need for the centripetal acceleration, right? Is just v squared over r, which is 20 squared over 3. And that's 133.3 meters per second squared. Same units as regular linear acceleration. So it's pretty good acceleration. For the second part, if we want the time to complete one revolution, then I'll just put it part 2 here. Then I would use that equation we just found up here for centripetal acceleration. So AC equals 4 pi, or it's pi squared, r over t squared. Now, t squared is the thing we want, or not t squared, we just want the t. And so I can multiply both sides of this by t squared, and I can divide both sides of this equation by AC. And that means over here, the AC's cancel, and on the other side, the t squareds cancel. And that leaves me with t squared equals 4 pi squared r divided by AC. And then the only thing I've got to do is take the square root of both sides, which means t equals the square root of 4 pi squared r over AC. Now, if this were just math, I would say positive or negative, but I obviously only care about the positive solution. So if I substitute in the numbers here, the period or the time for one revolution is 4 pi squared. I would leave it as that, and usually there's a button for pi in your calculator. I wouldn't round it to 3.14. The radius we're given is 3, and the acceleration we just calculated was 133.3. And that means that the period, if we put all these numbers into a calculator, is 0.942 seconds. Not bad for one revolution.